Good morning to all of you. I warmly welcome to Professor Mao and all the delegates on the second last day of this Indo-US Webinar and Lecture Series. So today it's day 8, and today we have the special lecture Professor Mao from Professor Mao, and another we have the surprise lecture. I have already disclosed the name of the speaker in front of Professor Mao. He is Dr. Shashank from University of Delhi. He will speak on the nanomaterial synthesis, and he will show the art and class of the synthesis aspects to fabricate the materials in different size and different shape, and what are the controlling factors. So today in the morning session we have the special lecture from Professor Mao. He always giving the very interesting talks on the different class of the science. So today he will speak on the exploration of wavelength conversion nanomaterials. So I request all the participants, so please be attentive today also, like in the past 1 week time. And we know actually this program was a very long program, and you have shown your lot of energy for your patient listening. So with this request, I request Professor Mao to please begin his lecture on the conversion of the nanomaterials. Thank you, Professor Mao.
Thank you, Dr. Ahmad. And let me share my screen. Okay, cool. Looks good. Okay. Yeah, I'm so happy, and this is my last lecture. While I really enjoyed the experience. So today I'm going to talk about the exploration of wavelength conversion nanomaterials. So you will see that what wavelength conversion is about, and also I will introduce you several types of wavelength conversion nanomaterials, and briefly connect this type of nanomaterials to their applications, so you will get a full picture of it. So let's start. I remember that yesterday Dr. Riaz mentioned how to get my publications. I think the Google Scholar is the most convenient way. I really like it, because every new publications, it will remind us, right? It always reminds us to confirm it. So this is wonderful. I don't need to spend time to manage everything. So Google Scholar already did that. So if you are interested, please go and to Google Scholar and find me, and I appreciate that. And if you have questions, we always can communicate by email, things like that. And so when we talk about, so let's get back to this this webinar. When we talk about the wavelength conversion, as I mentioned yesterday, right? There is a Stokes shift and a Stokes shift. That's about the wavelength conversion, right? So that's one thing, and so I won't go to the details because we already talked about this yesterday. But there is an important thing, right, for wavelength conversion materials, and how do we, if we want to further tune the luminescence spectrums, right? How do we do that? And also, the first question is, when we talk about the spectrum tuning, is actually there are several different aspects of that, right? It can be related to peak position shifting, right? It can be blue shift or red shift, right? It can be the intensity vary, right? The intensity, the peak intensity can change, and also the peak shape can change, right? And including the splitting or merging of the peaks as well. Those are the all the different aspects, and also the ratio of different peaks also a lot of times it actually tells us a lot of information about the materials and the structure, those type of things. So, related to this aspect, this type of materials is actually a lot of fun to study. And again, I will show you some applications aspect, you work in, it makes everything more interesting. So how do we tune the luminescence spectrum, right? So here I list 6 strategies, more or less, there are other type of terms to describe this, but more or less, they are quite similar. So I will start with this one because we are talking about the nanomaterials. The particle size control, particle size tuning. That's something we can do, and also it will change the luminescence spectrum. Doping level tuning, and then in terms of the composition, we can change the cations, and the anions, and there are new ways as well. It's called co-substitution. We can submit more than one cations or more than one anions, or it can be combinations of the cations and anions as well. It's called co-substitution, and also that will affect the crystal structure and the local environment of the dopants, right? Because we're talking about the luminescence here, the type of luminescent materials I'm talking about is the landslide doped or transition metal doped materials. And then, we can also tune the crystals, engineering the crystal structure. And the other thing is we are talking about the nanomaterials, right? We can use the core and shell structures. And I'll show some examples related to each of these strategies. So that's overall, right? These different strategies. And then, first I want to introduce you a couple of type of luminescence spectrum. First one is, yesterday we talked about the absorption spectrum, right? And then, then we got to the go through, the non-radiative relaxation, and then the luminescence, right? So this is, similar to our everyday life, right? We can jump up to stairs and then, take a few small steps and then jump down, right? So that's absorption. And then, we spend some time to talk about photoluminescence, right? Photoluminescence, basically, we use a light source. It can be laser, it can be a xenon lamp, it can be even X-rays. I mean, those type of light sources, and then use a photo multiplier mostly, right, to get the to take the luminescence, and so that's a photoluminescence, and then luminescence. This is something different, right? So luminescence is actually, we use the electron beam to excite our samples and then take the luminescence by using photo multipliers. So you can see the photoluminescence, how it's different from the luminescence, right? Basically, the excitation sources are different. And then there's another one, is called the up conversion. I will talk a little bit about this just in a little bit. I'll show you some examples as well. So that's, a few types of the luminescence. And then in terms of the applications, the luminescent materials, can be, especially nanomaterials, it can be used as field emission display, LED lighting, as I mentioned, discussed yesterday, bioanalysis, X-ray imaging, those type of applications. Here I just try to schematically show in some of those type of applications, right? So field emission display, this is related to the up conversion and for bioimaging, this type of applications, and also, combined with other type of materials, so it can be used as photocatalysis, photovoltaics, radiation indicators, those type of applications. I mean, the list can, keep going on and on, but later on when I talk about the specific type of luminescence and the specific type of metal oxide nanomaterials, I will show you some other type of other applications. So with that, this is what today I just gave a very brief introduction, so I hope that makes a little bit, we can spend more time talk about some examples. So I will start with the photoluminescence and the luminescence, and then after that I will talk about another type of metal oxides, related to their photoluminescence, radioluminescence, and then I will talk about another type of luminescent material. It's called persistent luminescence. And then last I will talk about the off-conversion luminescence. So yeah, I'll start with this again. Again, luminescence is you use the electron e-beam, and then this is actually then we can take the luminescence, in that case the luminescence. But this one, this one is actually a lot of times the luminescence is actually combined with electron microscope, and then so that way it can give high resolution as well, right? It can be combined with a scanning electron microscope or transmission electron microscope. And this is actually something we are familiar with, right? With electron microscope, right? A lot of times when we take ACM images, we use the secondary electrons, or we use the backscattered electrons, right? That's if we take EDX, is actually that's we get the X-rays, right, out of the samples, right? So this yeah, not every SEM instrument has a luminescence capability, but this is the attachment to it. Nothing really special, but I'll show you some examples of how that is done. I will get back to this first, the type of materials I'm interested with. I talked about this briefly a few days ago. So yttrium oxide basically. So we synthesize the yttrium oxide nanomaterials by both modern salt synthesis and hydrothermal synthesis. I will skip this, go through this quickly, but I already talked about the advantages, by the hydrothermal synthesis, right? We actually we made the hydroxide nanotubes, and then through the titration process, we get the yttrium oxide nanotubes, right? By using the modern salt synthesis, then we can easily make the yttrium oxide or erbium doped yttrium oxide nanoparticles. And so both of these methods are quite easy and simple. They are quite easy, robust synthesis procedure, and by each of these synthesis methods, we can control the morphology, and also we can control the doping levels. Especially the doping levels, I will show you further details. Right, this is what we do. Right, for example, the morphology, actually we can easily control them. From this image, you can see those tubes actually, have a very clean end. It's a very smooth surface as well. And then this one, you can see the lattice clearly, right? The nanoparticles. So this is what I'm talking about. We can control the doping level very well, right? So we did this type of X-ray diffraction, and actually use a single draw X-ray diffraction. So this type of XRD patterns are more actually more high resolution, and so we can really analyze the peak shifting very well, because in terms of the erbium and yttrium, right, their ionic radius is actually pretty close. So the single draw X-ray diffraction pattern actually can help us to determine this small shift of the peaks, right? And then eventually we can calculate the lattice constant, right? And then relate it to the yttrium atomic content in this erbium doped yttrium oxide nanotubes, and then we get this straight line. And that tells us actually, this type of erbium doped yttrium oxide nanotubes actually follow the Vegas law, which tells us that this type of nanotubes are single phase solid solution, and of course they are crystal, right? So that's one important message, right? So it's very detailed. And then the other thing is actually we also did the X-ray absorption studies of the erbium dopants. The first thing is you can see that with the different erbium doping levels, right? And we can see these peaks related to the erbium L3H at this position, and that tells us, erbium is actually trivalent doped, as expected, right? And then, from this E-train KH, and then we also can see this, and from both of this, the sense data based on the urban edge and the E-train edge, we can see that, this type of nanotubes, they all possessing similar chemical environment. And so that's one thing important. And then other than that, right, the other technique related to X-ray absorption spectroscopy is really to understand the dopant environment. So we use the X-ray, we use the XFs to do that. And then, of course, to do that, so we build these type of models. The first one is the erbium oxide. So around the, the erbium, here, here the metal is only erbium, right? And then for the erbium doped E-train oxide, then we build this mixed, this model with mixed E-train and the erbium, and then depends on their ratios, and then we can study, this the whole series of erbium doped E-train oxide nanotubes. So then by the program, and we really feed, this is the original data, right? Here I'm showing here, these are the original, the experimental data, and then based on the build models here, and then we can do the feeding. And you can see that, these models actually can describe this match, this experimental data very well. And here, from this, we can see that erbium and oxygen bond lengths, and then erbium bond lengths, and those are all, match with the this model. So that tells us, the erbium actually, the dopants enter the lattice of the E-train oxide, and then the erbium dopants substitute the E-train atoms, and then no E-train oxide clusters formed, right? Because if they are clusters formed, right, the surrounding of these erbium ions will be different, right? So that tells us, And then, when we look back to the luminescence, and then we can see that, these are, in a very broad range, right? When the samples are excited by 488 nanometer laser, and we can see, there are a few groups of the peaks at the different wavelength range. More importantly, if we look carefully, that's actually very important. These peaks are actually, they are quite a few sharp peaks, right? And so that is related to the energy levels of this the erbium, in the crystal environment, and we can match this very well. So, for example, here this is the ground state of erbium, and then once excited by 488 nanometer laser, and then you go to this 4F7 half energy level, and then through the non-radiative irradiation, and then it will go to the different energy levels, and then eventually it emit light at the different wavelengths. So here you see this is related to 870 nanometer, right? Related to this transition here, and then this one, and then 980 nanometer as well. So in this region, and then you can see 1150 is somewhere here. There are some very small peaks. That means this is not really a populated emission transition. 1250 somewhere here. You see these are the peaks here, and then most importantly is some peaks around this 1535 nanometers, right? So for both samples, we can see these peaks as well. So that's one thing important, right? And also this photoluminescence spectrum data is consistent with the results, with the X-ray absorption results we just discussed. And then More importantly, I want to look more closely for these peaks in this wavelength range. And here is is a zooming of those peaks, and then you will see that there are more than 10, around 10 peaks, and each of these actually we can exactly identify them, as I mentioned to you earlier. And if we zoom in this region, and then we will see that these are the transitions, right? Because for this 4i 13 half and 4i 15 half, if I go back to the previous one, right? This is if this is the urban ions in the not in a crystal structure, right? It's a free atom, and then it's only one energy level. But once it's doped in a crystal, depends on the crystal structure, and then that energy levels actually was split, right? And then both of these were split. That gave us so many fine peaks, right? And then because of the yttrium oxide has this unique cubic structure, so it has two sides. One is called C2, the other one is C3i, and that will further split. That's why you see there are 10 peaks here, but then there are some peaks I marked with surfaces here, and that is actually because they are at a different these sites. Okay, so for both nanotubes and the nanoparticles, we see both the same, right? Because that actually the very important thing to tell us is because this nanomaterials are highly crystalline. Only when it's highly crystalline and the samples are highly crystalline, then we can see these peaks individually like this. Er.Y has been widely doped into silica as a fiber, optical transmission fiber. So for that type of samples, then we only see a broad peak in this region. Okay, so that's the other thing to tell us. Other than that, we also look at the upconversion, right? So here you can see that the excitation is at 804 nanometer around that. And then we can see there is a gray emission and red emission, right? So this is what the upper conversion is about, right? You see this excitation is at longer wavelengths, that means lower energy, but the emission is actually at shorter wavelengths with a higher energy. And then this one is in the green region, and then this one shows the emission in the red region. And so how does that happen, right? For upper conversion, that's one thing, we always wonder, right? So this actually, this figure actually we proposed to try to explain, what really happened. So basically here you can see this is the excitation, right? So after the excitation, it could be possible give back, right? Emit, but a lot of times because this is for urban, and then it can have energy transfer. So that means the excited electrons can absorb another photon, and then it can be further excited to even higher energy level, right? So through some of this non-radiative transitions, and then then at a certain energy level, and then it would emit light at this shorter wavelengths. So that is the upconversion process. Okay. So and then for upconversion is also important, right? Here you can see that basically what I proposed here is the urban absorb two photons, right? And then it can be emit at this wavelength, for example, right? Or at this wavelength. So is this really, whether this mechanism we proposed here is correct or not, right? So if we want to confirm that, we can do some further study, right? Because this is just a proposed mechanism. So how do we do that, right? So there's one way, it's called the pump power dependent studies. So as I mentioned to you here, right, this is excited by a laser, right? For laser, we can adjust, the pump power. And then, we can see that how this pump power, how this integrated photoluminescence intensity is related to the pump power. So, so we see that, the pump power, when the pump power increase, and then we see that photoluminescence intensity actually increase. And then, yeah, so if you can excuse me, let me, one thing, and then the other thing is related to this is for the nanoparticles. Interesting thing is actually we can see the synthesized, it follows this trend, right? Excitation power and then photoluminescence intensity. But if we actually do a post-annealing of the samples, and then this photoluminescence actually could increase furthermore. So the reason for that is because, remember, right, for these nanoparticles, we synthesize by the molten salt synthesis. And the last step of that molten salt synthesis is we wash the salts away by water, right? And then we just dry, in an oven at a very low temperature, around 100 degrees Celsius. So in that way, certainly the surface of these nanoparticles still have some water molecules, physically absorbed water molecules, so by post-annealing, and then, we can get rid of those surface water molecules. And that's why, it gave actually this increase of the luminescence intensity. So, then the other thing is, it's really important for us to understand how stable this type of yttrium oxide nanostructures, stable with temperature. So we did this study, right? You see this is measurement temperature in this temperature range, and then we can see that the luminescence intensity is actually decreasing with increasing measurement temperature. And that's understandable, right? Because there's actually a lot of materials have this thermal quenching effect. But recently, there are some, many studies actually demonstrated that some materials actually have zero thermal quench. And my research group actually recently also have started some of this thing. I'm not going to present today, but that's one thing, even though I should say in general, there is a thermal quench for luminescence, but not always. And so that's another topic, if you are interested in that aspect, that's really interesting. And and then this is related to the cathodoluminescence I've been talking with you about. Okay. Yeah, I mean, here I marked, this is the cathodoluminescence imaging, this is the ACM imaging, and if I didn't mark, this, and a lot of times we may not be able to identify which one is the ACM image, which one is cathodoluminescence image, right? But the most important thing I want to say is each of these nanostructures, individual nanostructures, it shows that they show cathodoluminescence. Okay, and this is very important for field emission display, right? So that's why we did this study, and also we did some further studies, which I mentioned here at the bottom. When we increase the beam current, right, which related to the electron beams, right, actually the cathodoluminescence voltage increase at a fixed beam voltage. Okay, so that means that the electron beam voltage is fixed. We only increase the beam current, and then we observed that the cathodoluminescence voltage increase. Okay, and then in the other studies, we fixed the beam current, but we increased the beam voltage, and also we see the luminescence voltage increased. So that means this material is actually pretty responsive to the electron beam, right? So yeah, so far here we can kind of tell this each of these individual nanostructures they are all luminescent, right? Luminescent, and we did a little bit of study through collaboration, actually and really started the photoluminescence. Okay, so for example, here shows actually we zoom, we only excited the individual nanotube. Okay, and then we use a micro photoluminescence spectroscopy, and then we take the photoluminescence spectrum. And then you can see here, and also at the different temperatures. And then you can see this is a characteristic erbium emission. And so that really tells us, each of these individual nanotubes, actually, they are luminescent. Okay. In terms of the peak positions, there is no actually difference between the micro photoluminescence and the macro photoluminescence. Okay. So that's pretty much, the studies we have done in this type of erbium doped ethylene oxide nanostructures, with mostly photoluminescence, and also luminescence. And when we talk about the photoluminescence, we did, the examples of those nanostructures, and also we did the individual nanotubes. And so let's move on to the next thing, photoluminescence and the radioluminescence. And this is something I discussed earlier a couple of times, right? We actually developed this modern salt synthesis combined with the post-precipitation process. We will be able to make this type of pyrochlor nanoparticles. And here shows that we can tune the nanoparticle sizes, and then that affects, right, the quantum yield and also the decay time, right? So this is one thing I mentioned about how they tune the luminescence spectrum and by particle size, right? And then the other thing is I want to look into the composition, right? So here I'm showing the non-standard zirconate and the non-standard hafnate, right? So here is the luminescence spectrum we took from these two samples. And the black one is non-standard hafnate, and then this red one is non-standard zirconate. The difference is you will see the non-standard hafnate has much stronger peak here, right? And then for the non-standard zirconate, we actually in this wavelength region, we actually observed two peaks, right? And then if you look at the periodical table, right, zirconium and hafnium, they are close to each other, right? One on the top, one on the bottom, right? And then in terms of the ionic radius, they are so similar, right? So what makes this huge difference, right? So through collaboration and our collaborators did the DFT calculations for us, and then the other thing I want to mention is these are undoped samples, right? In general, then undoped samples, we don't think, they are normally there's no luminescence, right? So of course, not always, okay? Then, where the luminescence come from, right? So that's one thing we try to understand. And so, through the DFT calculations, it has been identified there are different type of oxygen vacancies in the band gap, and then depends on the band gap, and also depend on where the oxygen vacancy located, and then it will give this these different peaks. And then for non-standard zirconate, and then we see that, and this is related to the peak around 392 nanometers, and then for the peak around the 707 nanometer is from here, right? But then for non-standard hafnate, Yes, there are also oxide vacancies between the gap, in the band gap. Oops. But then the thing is, there are two peaks as well. But then this peak is at a much longer wavelength, and so with the instrument we have, and so we couldn't observe it. So that's that's what we obtained. And then the other thing is here. Now I'm going to show you for both of these host materials, we doped them with the European 3+, and then we doped them with the same European concentrations, and in this region, right? And then one interesting thing is you will see that first is for both the lanthanum hafnate and the lanthanum zirconate host, right? There is optimum doping level, right? About 5%. That's actually it's pretty consistent with the literature, and that's for European doping levels, right? And then beyond 5%, and then we normally will see the concentration change. And then another interesting observation is when the host is an lanthanum hafnate, okay, the quantum yield is always higher, right? And then when lanthanum zirconate is a host, right? So the question is why, right? Again, as I mentioned to you, right? If we look at the periodic table, zirconium-40, it has this electronic configuration, and then for the hafnium, and it has this electron configuration. And the most important thing is when their coordination number is 6, and the zirconium-4+ is actually has a little bit larger ionic radius than the hafnium 4+, right? So to understand this is, and of course, right, the ionic radius is only one factor, right? And then hafnium 4+ definitely has 32 more electrons than the zirconium 4+, right? So that could affect, because of the even though the size is quite similar, but because of the extra electrons for hafnium 4+, right, that could affect the crystal field splitting of the European 3+ ions, and that because of the change of the charge cloud of the European 3+ ions, that gave us different quantum yield. So that's that's how these experimental results being explained. So the other thing I want to mention is, what's the difference between the photoluminescence and the radioluminescence, right? So as I just discussed so far, right? When we talk about the photoluminescence, normally the excitation source is by UV light source or by visible light source, right? Or by either the xenon lamp or the laser sources, right? But for radioluminescence, is actually the excitation energy is much higher. Okay, it can be from X-ray, it can be from gamma ray, those type of resources. And then because of the huge amount of energy, right? So the excitation is not by exciting the activators, okay, basically the dopants, right? Not like in the photoluminescence. So for the radioluminescence is mostly excite the host materials, and then those photons will go back, eventually get back to the activators, and then from the activators it will luminescent. Okay, so in that way the mechanism is quite different because of the energy difference. So why radioluminescence is important, right? So it's actually related to the scintillation detectors, especially the ionizing radiation scintillator detectors. And is something widely used in hospital, right? For even when we go to see dentists, right? The first thing is what the dentist will take a photo of our teeth, right? So there is something, part of that is actually related to the radioluminescent materials. And that is how, right, because X-ray is so strong, right? So we don't want it directly, so the X-ray hit on a film which has phosphorus, and then that will transfer to the film, and that's how we get the images, right? And then the other important thing is related to the security, right? Now when we go to airport, we'll go through the security check, right? So that is also related to some of those detectors actually related to the radioluminescent materials. So again, get back to how we tune the luminescent spectrum, right? So I mentioned to you earlier, the particle size and the crystal structure engineering, so we did one study and demonstrate that we can do that, right? So again, here we used gadolinium half-late 5% doped European 3+, and then we synthesized these nanoparticles by the modern salt synthesis process I just described at 650 degrees Celsius, right? So and then because of the ionic radius of the gadolinium half-length, so this material actually these nanoparticles has a disordered fluoride structure, and then the particle size is about 7 nanometers. And then with those nanoparticles, we heat it up to near them at 1100 degrees Celsius and also 1300 degrees Celsius. So during that process, we see that the nanoparticles keep increasing, and it's actually up to 50 nanometers. And also, eventually, these nanoparticles have the ordered pyrochlore structure, right? So there's a particle size change, and also there's a crystal structure change. Okay, and then we did take the radioluminescence of these two samples, and then you will see that from the original nanoparticles, and then it gave the radio emission. And then for this pyrochlore nanoparticles at 50 nanometers, it gave the orange emission, right? So that tells us, we can tune the radioluminescence of these materials by particle size and engineering structure engineering. Okay. This is important. This can be served as a strategy to design advanced orbital electronic materials. So that's about this one. And then the other strategy I've been talking about, the Cauchy nanoparticles, right? So this is really something very interesting. Well, it's not as easy as we thought, to make the Cauchy nanoparticles for this type of metal oxides. Okay, I know for those of you who work with quantum dots, people do that, make Cauchy nanoparticles quantum dots about, right? So often nowadays. So, but for this type of complex metal oxides, it's not so easy. But let me explain, why we believe this Cauchy strategy will improve the luminescence, right? Especially, when we talking about the radioluminescence. So here, the design is like this. The core is actually the real doped luminescent nanoparticles, and then we coat it with a shell, and that shell is not doped. And also for radioluminescence, it can be, we try to pick a shell material which can absorb the radiation better. And so, and then the other thing to consider, this type of core shell combination is that the band structure of the shell material is actually larger and also cross the band structure of the core material. So when we excite this type of core shell nanoparticles, right? So we work at the excited charge carriers, right? For the core material, then it will luminescent, right? But the advantage of this core shell material is the shell also can be excited, right? Can generate those charge carriers. And then because of this type of band structure design, and those charge carriers will transfer to the core material, and that will help to increase the photoluminescence, right? So that's the design, and also because we know that core this type of nanoparticles, in general, they have a lot of surface defects, right? So that is not ideal for luminescence. So to eliminate the surface defects, and then it's common strategy to coat the core material with the shell material. So that's the other consideration as well. So how do we make this core shell nanoparticles? Especially our core nanoparticles. Nanoparticles are synthesized by our modern salt synthesis method. They are no surface functional groups on the surface, right? So that makes the shell deposition more difficult. So how do we did that? Eventually, so because of the shell material here, we use the hydrogen oxide, right? So initially we thought, if we use the sol gel process, we should be able to coat the core material by a gel, and so by sol and gel, right? And then through calcination, we should be able to make this type of core shell nanoparticles, right? But then we found out that this doesn't work. Okay, the reason is, this shell material actually it doesn't want to stick on the surface, right? It forms its own it forms its own face, and so we've been thinking about how do we get this shell material on the surface. So we thought, first we need to surface functionalize the core material, right? And while at the same time is we want to make this simple. We don't want to use those bulky organic compounds, right? So so the one thing we did is, we used the hydrothermal process, to coat it with the carbonaceous materials. And then, because carbonaceous materials actually has a lot of hydroxy groups, and the hydroxy group, that's the idea for the sol gel coating on the core particles. And then, once we done that, and then we do the calcination, and then we will be able to get these core shell nanoparticles. So, so here, we show a EM image, and it really show that we did get the shell material on the core material. More importantly, and we did the photoluminescence in terms of the quantum yield. We can see that at a certain molar ratio of the shell to the core, and we can increase the quantum yield by about 2 times, right? It's understandable, right? If we keep increasing the shell material, as I mentioned here, the shell material is not luminescent by itself, right? So that's why when we keep increasing the shell material, the ratio of the shell to core, and then we will see the quantum yield sort of decrease, right? And then the same happened to the radioluminescence, and it's also about when the ratio of the shell to core is about 2, and then we get the highest integrating radioluminescence intensity. So that's the other aspect. Yeah. So with that, that's one thing, and then I will talk a little bit about the one type of application recently we've become more interested, right? So it's about how do we use luminescent materials for to measure temperature, right? We know how important temperature measurement is to us, right? For our health, for any reactions, for any instrument, right? It's a very important parameter, right? So, but then there are some challenging situations. The thermometers we currently using doesn't work, right? For example, here, one example is for this moving parts. How do we measure the temperature, right? If we want to measure the temperature in the real time, right, it's difficult. And also, for those of you working with the chemical industry, you know that, right? With the reactor, even we do synthesis in a lab, you know, in our beaker, right? Do we know that the temperature is uniform in our reactors? Probably not, right? So how do we measure the temperature like that? So, so that's one thing, you know, related to the luminescence thermometer, right? Especially for some environment, it's for harsh environment, right? It's difficult for us to put the thermometers in there, right? And also, if we want to get a high spatial resolution, right? The regular thermometer doesn't work that way, right? If we want to get a rapid response in a non-invasive operation, and how do we do that, right? And also, if we want to reduce air in a reduced areas and with a submicro metric resolution and with a higher accuracy, right? So how do we do that? So that's what we want to use as luminescence thermometry. So I want to show you, and so with especially with luminescent nanoparticles, right? And then we will be able to achieve that. So as I mentioned, you know, in the past, right, a couple of days, this type of pyrocolloid materials actually have very good thermal stability and among many other desirable properties. So we thought, you know, we want to use this Lancelot half-net as a host, and excuse me, and then doped with 5% European. And then we measured the luminescence, you know, at different temperatures, and then, you know, we plot the normalized intensity of a specific transition, and when we will see that the intensity actually showing this trend, right? You know, is decreasing, and then, you know, then we will be able to calculate the sensitivity, right, of the temperature. So here I'm not going to tell you how exactly the details how this is done, but and then we can calculate the maximum relative sensitivity and in what temperature range. And from here, you can see this one is our samples, right? And this the other ones are reported in the literature. And you can see that, you know, the relative sensitivity of the samples is actually pretty good, and also in a quite wide temperature range. Right, so that's two important parameters, right, for thermometer, right? You know, in a wide temperature range, you know, with a high sensitivity. So this material demonstrates that, right? And then the other type of design is you see here. There is only one dopant. We only depend on the luminescence from this dopant, right? So then there are another strategy is, we add, actually we co-dope a material, and one of the dopant is actually the reference signal along the temperature, and then the other dopant actually acts as a probe, can provide the probe signal, and and then we can also get the thermometer sensitivity, right? So this is something new we are working on now. You know, we dope it with turbine. So this is because this is real earth element, so it's, you know, it's more temperature insensitive, right? You know, and then this this transition metals, manganese is more you know, temperature sensitive. So with that, you will see that, you know, then we can see that, you know, so these plots we actually represent, this is for the manganese, and then this one's actually for the turbine, and then, you know, then we can calculate the sensitivity, and here is our result, and then, you know, this is our feeding, and we also got the relative sensitivity and absolute sensitivity, and then we we compared with the literature, then we can see that, for our samples, it has a reasonable good sensitivity, while our samples are nanoparticles, right? And the other samples they are not, right? That's the advantage. And the other thing about this, other than the spatial resolution and the temperature resolution is also very important, right? Just like our regular thermometer, right? If we can measure the temperature accurate to 1 degree or to 0.1 degree, right? That makes difference, right? So we can see that our samples actually shows quite good temperature resolution, and it is about 0.5 degree, depends on the temperature range, right, of course. So that tells us, and then why this happens, right? So we try to understand that, propose this mechanism for the terbium, right? Because the transition is quite somewhat stable, while for the manganese, the electrons can be excited, and then to this high excited energy levels, right? And then at the same time, it's because of it's more sensitive to the temperature. That's why the transitions is so temperature sensitive. So that gave us another example in terms of the luminescence thermometer. And so to summarize here, initially this type of pyrochlore nanoparticles actually synthesized by this modern salt synthesis, and I mainly focused on this different strategies to tune the luminescence, right? I showed some examples, in this couple of days, right? Today I'm mainly focused on the luminescence thermometry, but yesterday I talked about, how we use it for lighting, and before that, for this type of materials can be used for nuclear waste containment. Right, so the next one I want to show you is persistent luminescence. I think I need to cover it up a little bit. So persistent luminescence, luminescence, right, is in general, it's a luminescence process, happens in like microseconds or in nanosecond. But persistent luminescence is different from that, okay? Which is this type of materials actually they can emit light in the UV-Vis and near IR spectral region for minutes, hours, or even days after, okay, ceasing the excitation irradiation, right? So how this would happen, right? So the current most popular explanation is so in our host materials, there are some traps, electron traps, and those traps will store the photons. I mean, then and then once the excitation irradiation stopped, and then those photons will get back to the conduction band of the host material, and then eventually it will transfer to the activators, and then from the activator it will luminescent. Okay, so that's the mechanism for that. And then this type of materials, has a lot of potential applications, right? For example, the emergency signage, right? And recently, people actually, proposed that, on our street, right? Especially if it's a rainy day and it's a light time, right? A lot of times, whoever we drive under those conditions, we know how difficult, right, for us to see the road, especially if the roads are curvy, right? Or up and downs, right? It's so difficult. Right? The idea is if we paint these roads with this type of persistent luminescent materials, right? So those persistent luminescence will absorb light from sunlight during the daytime, right? And then in the nighttime, then it will luminescent, right? So we can see the roads. And also recently, it has been explored for fingerprint. And then the other thing is we know that, right? For solar catalysis, right? Then we have to it only works during the daytime, right? So in the nighttime, then those photocatalysts doesn't work, right? And then how do we overcome that, right? If we can store some of the solar light, during the daytime by persistent luminescence, right? And then during the nighttime, and then the photocatalysis still works, right? And so that's some of the ideas. And so we looked into this type of phosphorus, chromium doped zinc gallium, and this has a so this is also a well-known material. It has a spin-off structure, right? So I will skip this part, in terms of. But one important thing is the chromium is also interesting, right? It normally emits light around 695 nanometers while this transition of a chromium. And the more important thing is the match with the optic window for biological tissue. So this type of material is very promising for bioimaging, right? So first we thought about how to synthesize these nanoparticles, especially for bioimaging, for bio-related applications, right? We need to make these particles very small and uniform. If it is sub 10 nanometers, that's ideal. So we developed this synthesis technique. Basically, this is called the biphasic synthesis technique. For those of you working with metallic nanoparticles, you will know that, right? It has been used to make metallic nanoparticles, this biphasic process. But it's, at that time, it happened used to make metal oxide nanoparticles. So we thought about, to make the precursors in the water phase. That's easy, right? And then it is also a basic condition, especially, when we heat it up, the pH will increase. And then these nanoparticles will start to nuclei and nucleize and then grow at the interface. And then, this nanoparticles will transfer to the organic phase, and then the growth will be quite slow. And that makes these nanoparticles quite uniform. So that's the synthesis process. And then eventually it worked. And you can see that, the nanoparticles are small and quite uniform. They are single crystalline, and it matches with the spinel zinc gallium structure. And then we look at the excitation and emission spectrum of these nanoparticles. So you can see that these peaks are related to this peak related to the oxygen gallium charge transfer band, and then these two peaks are related to the chromium the 3D and 3D transitions, and then this is the emission from the chromium 3+, and so it tells us, right, definitely is luminescent, but more importantly, whether it's persistent luminescence or not, right? We did the study. So we excite this type of nanoparticles by 254 nanometer UV lamp for 5 minutes, and then remove the UV lamp, and then we take the luminescence, right, photoluminescence, and you will see these nanoparticles actually shows the luminescence even after 60 minutes, right? So this curve shows there is no nanoparticles. You can see that, right? So definitely it shows the persistent luminescence. And then we also use this for bio indicators. And then we can see that, we did see some red luminescence from the cells, with these nanoparticles. So yes, okay, this biphasic synthesis is good, and we can get the small nanoparticles, right? But then these nanoparticles are coated with some organic ligands, right? We still don't want that. So we thought about, how about we use hydrothermal synthesis? So this is what we did, and with hydrothermal synthesis, the precursors are similar, and then we use a base to adjust the pH. So eventually, we could form the nanoparticles. In literature, and the people use the sodium hydroxide and the ammonia. And so with, then the nanoparticles synthesized in literature, they are not uniform because the because the high pH, the initial high pH, right? So what we did is we think about, oh, how about, we use urea to replace ammonia or sodium hydroxide. So when we mix everything together, right, the pH, at room temperature is not that high, right? Only when we heat it up, then the pH will, start to further increase, right? So that's what we did, and then also, so that's what you see here, right? The curves here, this is the nanoparticle synthesized with ammonia as the base, and this is with sodium hydroxide as the base, and this is with urea as the base, and then you can see that the luminescence, increased, right? And then further, we also add, let me show this. We also add ammonium nitrate to it, right? So because we said, ammonium nitrate also could better adjust the pH of the reaction, and then you will see that, the luminescence further increased. And then this shows the persistent luminescence. You can see that, how, further we improved this persistent luminescence by our synthesis process. And then we got to, quite a nice publication for this last year, and because of this work. And then we also did some imaging using this type of nanoparticles, and you will clearly see that, these are the cells, right? With our nanoparticles, and then we can clearly see this. Right? Of course, these are with the different scales, and so with the details here, but what the important thing is this can be used for bioindicators. So far, I've been talking about how to improve the luminescence of these nanoparticles, right? During the synthesis process. And also I talked about, we use the modern salt synthesis to synthesize many metal oxide nanoparticles, right? Nanomaterials. But we're also wondering, right, for the post-synthesis process, can we use modern salt to do that, right? So instead of direct annealing, right? So this is something what we did, right? These are the chromium over the zinc gallate nanoparticles, right? We synthesized by the hydrothermal synthesis, right? And one way to improve the luminescence and the persistent luminescence is by direct heating of these particles at 600, for example, at 650 degrees Celsius, and then we get this type of nanoparticles. Okay, the nanoparticles, normally there is a size increase, and also agglomeration of those nanoparticles, right? So we thought, how about we do this annealing in modern salts? Okay, so this is what happened. Okay, then the particles doesn't increase that much, the size in this, and also there is agglomeration free, and that really helps us, right? And while the luminescence and the persistent luminescence, for the particles after this two annealing process shows quite similar. So that's important, one important aspect, right? And yeah, so you can see here, right, in terms of persistent luminescence, after these two annealing processes, they show quite similar. And so that's really, promising. So recently, this paper just accepted by the chemistry, a European journal, and so now it's in the press. So the last one I want to show you is related to up conversion. I already mentioned somehow about the up conversion, and so the up conversion, right? Basically, the regular luminescence, right? The phosphorus absorb higher energy and then emit at a lower energy, that is longer wavelengths, right? But for some materials, actually, they can absorb photons continuously and then emit light at a higher energy. That is up conversion luminescence, right? So it's under Stokes process. So it's just like, you can jump twice up and then jump down once, right? For example, and why this is important, related to bioimaging, and so we can excite the materials um, um, at um, at longer wavelengths, and so that will, especially in the biological windows, and that will really help to enhance the, the resolution. And so that's so how do we do that, right? So we tried a couple of strategies. I will show you a couple of examples here now. So one thing we did is we co-doped lithium to this type of nanoparticles, for to enhance the upconversion. So for example, here, we doped the erbium and the ytterbium into national circuit, and then we further doped the lithium, and it depends on the lithium concentration, and we can see that. And here shows actually it's a personal structure change, but the most important thing I want to show you is how the lithium doping level changes the luminescence, and the upconversion luminescence. So here, right, you can see that the excitation is 980 nanometers, and then emission is in this green and red region, right? So here shows that the lithium concentration, how the emission in this varies with the lithium doping concentration, and you will see that the green emission actually shows 14%, a 14-fold increase, while the and also at a similar lithium doping level, and then the red emission could reach 18-fold increase. So that really is quite a lot, okay, in terms of luminescence. If we can increase more than 10-fold, that's a lot. And then the other study, we worked recently is related to how the thermal annealing actually changes the luminescence, right? So here you can see that this is chromium co-doped zinc galate, co-doped into the ytterbium and the erbium doped zinc galate nanoparticles, right? So for the synthesized this type of nanoparticles, if we excite it by 256 nanometer UV excitation, and then we get luminescence like this. So we get near infrared red emission, right? This is similar to what I showed you earlier, right? When I talk about the persistent luminescence of this type of materials, right? One important thing is, okay, so because this is ytterbium erbium doped, so we also look at it as upconversion. We look at it as upconversion. So we excited this material by 980 nanometer infrared, and then we look at it. We saw the red emission and the green emission, right? So this emission is good, right? But then, if once we further near these nanoparticles at 700 degrees Celsius, and then we take the upconversion again, and then what happened? Now we only get a singular red emission, and then the green emission is almost disappeared, right? What makes that change? So, right, so and also depends on the annealing temperature. This peaks actually, the ratio of these peaks actually, also varies. And we found that 700 degrees Celsius is actually the optimal annealing temperature, right? So our proposal is like, when we just synthesize these nanoparticles, okay, the dopants actually are not uniformly doped into the nanoparticles. And most likely, the dopants actually will stay on the surface. And when we did the annealing, and then the dopants will migrate into the nanoparticles and also be better distributed in the nanoparticles. So that helps to increase the luminescence. And of course, and then this is what we propose in terms of, why there is only red emission. So because of the time, I will not go to the details about that. So to summarize, what I talked with you, is I showed you some, examples related to photo and radioluminescence. Mostly use this pyrochlore, as the example, and also I showed you some examples with the medicinal luminescence, right? Mostly based on the chromium of the zinc gallium nanoparticles. And then the other one is related to the optical motion, and then with different host materials. This is actually two. These actually are two covers of these two aspects, and I believe both were published last year. So that's something, I designed these covers, during the pandemic time, so that was, some small accomplishment, achievement. Then, yeah, really, again, I really want to acknowledge, my dedicated research group and in the past years, and also, appreciate the collaborators and also funding agency. If there is any questions and comments, please, I would be very happy to, answer any questions.
Thank you, Professor Mao, for the nice presentation. I would like to invite Dr. Ufana Riaz to please, if there is some query from the participant side, you may please put up in front of Professor Mao. Dr. Riaz.
Hello, Professor Mao. I hope you're doing good.
Yeah, definitely.
Okay, there are questions from the participant side. The first question is based on the insights. Could you please give insights into the use of luminescent materials in diagnostic and curing of diseases in humans?
Oh, okay. Yeah, that definitely, is a very exciting area, and it's also very hard research area. There are a lot of study on that. In the past years, I haven't really involved that much. But that's definitely one thing I want to involve much more, because it's related to, one is related to our health, right? If we can contribute to that, and that's definitely one important thing. And then the other thing is, related to the funding opportunity, right? Because of it's related to our health, and it has a lot of funding opportunities as well. So that's one thing I'm working on now, and I work with several colleagues. It's very promising. I think we would get some funding very soon. Yeah, so related to this, if any of you are interested with that, I think this is a wonderful research area. Of course, there are challenges, right? Because one is related to the live subject, right? That makes more challenge, and also there are more regulations to do that. So that's something we need to be aware. And also sometimes we take some extra time, right, in the planning.
Okay, so do all the molten processes, aerobic or anaerobic, affect the luminescence efficiency?
Oh, so far we try to make the modern salt synthesis as convenient as possible. So the modern salt synthesis we always do it just in air. But technically, we can do that on the inner atmosphere. That's definitely, I don't see any reasons for not doing that. But how that affects the luminescence, I think depends on the system, right? So and also depends on the luminescence mechanism. So I didn't present that actually. If it is related to the oxygen vacancy, luminescence, just like I showed here. Let me see. Just like I showed here, if the luminescence is actually related to the oxygen vacancy, I think if we synthesize the nanoparticles in inert atmosphere or under hydrogen is actually it could further increase the luminescence. So we actually have some results on that aspect. But what we did is actually we did the post annealing in reducing atmosphere, not during the molten salt synthesis. But I believe if we can do that, if we do that during the molten salt synthesis, it should have a similar effect.
Yeah, it is. I mean, it's fair enough. So how could we control the issue of toxicity when we are using these luminescent materials as probes in bioimaging?
Yeah, that's always a concern, right? That's why I said, for bio-related research, is always these extra challenges. So one thing I think, compared with, in general, compared with quantum dots, right? The material we are dealing with, one is they are metal types, right? So many of these metals are not those type of heavy metals. So we believe this type of materials will be more friendly, and and also we try not to use those known, those elements, or the compounds, with known toxicity. But of course, one thing we cannot avoid is, we are dealing with nanomolecules, right? If there is some certain aspect, toxicity aspect related to nanomolecules, right? Then we have to consider, other strategies to avoid that.
How could we control the problem of autofluorescence that we observe in biological tissues? I mean, how could we assure that the signals that we are getting from the nanoparticles through the luminescence emission is from the particular cell and not any backscattering or autofluorescence from biological tissues?
That's a very good question. I didn't, because of the time, I didn't mention that. So this persistent luminescent materials could be a wonderful solution for that, right? So related to that, we can excite this type of nanoparticles before we do the imaging, right? So when we do the bioimaging, and then we only need to consider the imaging part. We don't need to worry about the excitation part. And then the other one is related to the upper conversion. So because we can excite, okay, here is actually the slide. We can excite the samples, through these biological windows. So that's why recently, there are more studies to looking for this type of upconversion materials, especially in the near infrared. Yeah, very good question.
Okay, then how could core shell nanoparticles help in controlling luminescence? I mean, how could we obtain different colors of desired region using core shell nanoparticles? Is there any method to control emission luminescence in using core shell morphology?
Yeah, so one easy thing to think about is, to use a different dopants, right? and that will give us a different luminescence, right? The core shell strategy, I showed here is basically try to improve the luminescence, enhance the luminescence. I think technically it could tune the luminescence as well, but because of the constraint and stress, right? Have on these nanoparticles, and it depends on the particle sizes as well, right? That's definitely something need to further study, but before we can do that, and then we have to have very good control of this type of nanoparticles in terms of both the core size and the shell size. So yeah, that could be a very interesting topic, but I think now there are some challenges, at least for this type of metal oxides. And the one type of materials being studied a lot is the fluorides. For example, the sodium nitrogen fluorides, those type of nanoparticles. And the people can do the core shell, and the core shell structure, those type of nanoparticles. If you are interested, you can look into that.
Then what about photo bleaching? I mean, how much photo bleaching is there in these nanomaterials, and how can that be tackled?
I think that's one thing. Let me see. I think I talked about this 2-3 days ago. The one one unique thing about this type of inorganic materials is we don't absorb the photo bleaching like the organic luminescent materials. Because the unique structure, right? This type of inorganic, especially the metal oxides, they are quite stable.
So what if we combine organic and inorganic hybrid structures to design luminescent materials? I mean, will it be more feasible as compared to pure inorganic?
Oh yeah, wonderful. And again, it's a wonderful idea. There are some studies on that aspect, but mostly the organic part, it is used as used to absorb the excitation light, because this absorption band for the organic materials are mostly pretty wide. So they absorb the photons and then transfer the photons to the inorganic materials. And then because inorganic materials, the activators are more secured, and also in a more stable environment. So the luminescence from the inorganic compounds are sharper. So that's why, and also more in certain ways they are more efficient in terms of the emission part. So that's why recently there are some studies on that aspect. So try to get the better part from both.
So is it, feasible or advisable to increase the quantum yield of such materials to obtain better emission?
The quantum yield is always here. Some people always want to get a higher quantum yield. To achieve the unity, that's always the goal, right? That basically, there's a lower energy wastage, right? Yeah.
Okay, Professor Mao, it was a wonderful discussion, and on behalf of all the participants, I would like to thank you for this presentation. It was an appealing presentation on the exploration of wavelength conversion nanomaterials. It's a frontier area of research on advanced materials, and I must say the diversity of your lectures is amazing and it cannot be expressed in words. Especially the luminescence aspect of functional materials. I mean, it gives a fundamental aspect of designing such advanced materials. You've given a very remarkable presentation about the basic concepts and the advanced techniques that have been used. Your work is simply amazing and inspiring to all the participants, and we look forward to meet you soon, Professor Mao, maybe in some offline conference very soon. And we would love to meet you in person and discuss all these advanced functional materials and their technical aspects and their applications in future. Thank you for being with us. Thank you so much.
Thank you. Yeah, I look forward to meet you all.